In the previous video I mentioned that the worst case complexity of an algorithm is represented using the big O notation. But what exactly is big O notation? Let's understand in this video. If I have to explain in very simple terms, big O notation describes the complexity of an algorithm using algebraic terms. The big notation has two important characteristics. One, it is expressed in terms of the input. And two, it focuses on the bigger picture, without getting caught up in minute details. Let's understand these 2 points under the context of time complexity. We can then extend the knowledge to understand space complexity. Alright, let's calculate the worst case time complexity of our first program. I say program because the algorithm has already been implemented with JavaScript as a language. The algorithm is to find the sum of the first n natural numbers. We have an input n and the function will return the sum of all the natural numbers from 1 to n. For example, summation when called with n is equal to 4 will return 10. We already know we can calculate the absolute running time of an algorithm, and hence that cannot be the time complexity. What we do instead is count the number of times a statement executes based on the input size. Let's do the same for our program as well. A program has 3 main statements to execute: line 2, line 4 and line 6. For the loop is just a repetition of line 4. Now given n is equal to 4, let's calculate the number of times each statement is executed. Line 2 executed only once, line 4 however executes 4 times, I is equal to 1 to I is equal to 4. Line 6 again is executed just once, so the total count is 4 plus 2. I say 4 plus 2 because we can generalize it to n plus 2 where n is input to the function. If n is equal to 4, total count is 4 plus 2. If n is equal to 10, total count is 10 plus 2. If n is equal to 1 million, total count is 1 million plus 2. Our time complexity is dependent on the input size, and this is the third characteristic I mentioned a minute ago. Big O is expressed in terms of the input. The second point is that the big O focuses on the bigger picture without getting caught up in the minor details. Let's plug in a few values to n and understand this point. If n is equal to 100, n plus 2 is 100 plus 2. Similarly, we have 1000 plus 2, 10,000 plus 2, and as the input grows to millions, it is millions plus 2. At that point, the plus 2 is very insignificant. We can actually drop it. N plus 2 can be approximated to just n since n contributes the most to the total value, and not the additional 1 or 5 or 50 extra steps. Or in our case 2 extra steps, you don't have to get caught up in the smaller steps, that don't affect the performance as much as the others. So the worst case time complexity, which is also referred to as just the time complexity of our summation algorithm, is big O of n, which is referred to as linear time complexity. What this means is that as the size of the input increases, the time complexity also increases. Hopefully you now have the good idea of what the big O notation is. Now you might ask, do I have to calculate the count line by line to determine the time complexity? Well, you could, but you can also perform some safe calculations. Anytime you see a loop in your algorithm, most of the times you can safely say the time complexity is least linear. Of course, there are exceptions, and we will look at them throughout this course. But the loop's worst case is when it iterates over the entire input, and hence the time complexity is linear. If n is equal to 10, the statement will be executed 10 times in the worst case. Here is another algorithm for the same problem. Summation of first n natural numbers, the time complexity of this algorithm is O of 1, which is called constant time complexity. Irrespective of what the value of n is, line 2 is executed only once. Once you get the hang of it, it becomes easier to analyze the time complexity, for example. If there are two nested loops, the time complexity is quadratic. Once again, the big O notation drops the less dominant terms. If you calculate the complexity to be 3n squared plus 5n plus 1, we narrow that down to just n squared and call it quadratic. 100 million squared is so large compared to 5 into 100. Then we can drop the later term. Now, if there are 3 nested loops, it is cubic. If the input size is reduced by half every iteration, it is logarithmic. What we will be doing is determining the time complexity of the various algorithms we will be looking at throughout the series, so you will slowly but surely get the hang of it. Let's quickly talk about space complexity. The idea remains same. If the algorithm doesn't need extra memory, or the memory needed doesn't depend on the input size, the space complexity is constant. An example would be sorting algorithm, which sort within the array without utilizing additional arrays. You can also have algorithms with linear space complexity, where the extra space needed grows as the input size grows, and you can also have algorithmic space complexity, in which case the extra space needed grows but not at the same rate as the input size. Typically, you would find algorithms with these 3 space complexities. Also, it is common to solve with quadratic time complexity. Quadratic space complexity is something you should try to avoid. Let me go over a few more points that you should keep in mind before continuing. The first point is that multiple algorithms exist for the same problem, and there is no one right solution. Different algorithm works well under different constraints. You should always understand the problem statement before determining which is better. The second point is that the same algorithm with the same programming language can be implemented in different ways. We now have modern JavaScript features we can use to simplify the code we write. So what we learn in this series might be slightly different to what is out there. It doesn't make it an incorrect solution. Finally, when writing program at work, don't lose sight of the big picture. If you are writing a function that is called thousands of times every minute, sure, go ahead and optimize the code. Rather than writing clever code, write code that is simple to read and maintain. Alright, that is pretty much what I wanted to cover in this video. In the next video we're going to take a look at objects and arrays in the context of big O notations. Before we start solving problems and writing code, it is important to understand the big O and of object and arrays operations. So let's take a look at objects and array operations in the next video. Thank you for watching, make sure to subscribe to the channel, and I'll see you in the next video.